the summary is on the screen. We have basically for static failure, we have a number of theories. And the first one is the maximum principal stress. And it says that you have to find the three principal stresses, 1, 2, 3, and then you order them, and then you find the maximum one of them, and you equate it to the yield stress, and that gives you the boundary. And if it is 2D, we have only two non-zero stresses, sigma A and sigma B. So sigma A and B are the non-zero stresses from the principal stresses 1, 2, 3. So the third one is 0 if sigma 1, sigma 3, let's say, is 0 if we have plane stress conditions. So in this case, the yield surface is a box, exactly a box that is bounded by the yield strength of the material. Now, the next one is the maximum shear theory. And again, we want to find the failure boundary or the yield boundary. And the criterion is based on the maximum shear stress, which is in tension, which we know is equal to sigma 1 over 2. And then in tension, when sigma 1 is equal to the yield strength, then we have plasticity. Then we conclude that the maximum shear stress should not exceed half of the yield point, which translates to the difference between the maximum stress and the minimum stress is equal to the yield strength of the material. So again, if you have three stresses, one of them is 0, then you have two left that are non-zero, A and B. So depending on where the 0 is in relationship to the A and B, it could be at the end, could be in the middle, could be in the beginning. And depending on these kind of inequalities, then we get three cases, 1, 2, 3 that I have in the lecture. Two of them, 1 and 3, are basically in quadrant 1 and quadrant 3. And then the second one gives us the condition that sigma A minus sigma B is equal to S yield, which is the equation of a straight line. So this we get, roll it up here. We get the boundary to be this here, and then the straight line here, and then we get a straight line there. So these are the three boundaries that talked in the lecture. And usually we get the coordinates of a point as in homework assignment. And the point will have, this is the sigma A and the sigma B, the two non-zero stresses. And this is the load point is right here. So the load point, if it's inside, it would have a factor of safety as in problem 521. It would be the ratio of this length divided by this length. That would be the factor of safety. And if the point is exactly on the purple boundary, then the factor of safety is equal to 1. If the point is outside, then we have a factor of safety less than 1. And then we complete the rest of the boundary by symmetry, because we don't have any reason to say that compression is different from tension for a lot of ductile materials. So that would be the yield surface or the Tresca criterion. The next criterion is distortion energy theory. And here we decompose the stress field, which is represented by sigma 1, sigma 2, sigma 3, to two parts. One is an average component, and one is the excess from average. So the average is 1/3 of the sum of the three principal stresses, and then you compute the energy that is stored in the average and the energy stored in total, and you subtract this minus that to get the distortion energy. So the distortion energy is the end result. And failure is based on the distortion energy exceeding a certain level. So without going into the details, the end of this game is that we can summarize the process in constructing an additional stress called effective stress, sigma prime or sigma effective or sigma von Mises, which is the differences between the three stresses in permutations, as you can see here with the squares, and then you take the square root and you divide by square root of 2. So that von Mises stress should not exceed the yield strength of the material. And then what I wanted to add here is that sigma prime, you don't, like if you have like a complex loading condition like bending and torsion and axial force, then there will be another step, which is conversion of the forces to stresses. You know, the torsion is going to give you a shear stress, and the bending is going to give you an axial stress, and so forth. So that conversion would take some labor, some time, but it usually doesn't give us principal stresses. So the step after this one would be to convert the stress state to its equivalent principal stresses. And that we use the Mohr circle, for example, to do that. So to get to use sigma 1 and sigma 2 and sigma 3, it could be laborious because number 1, I have to convert forces to stresses. Number 2, I have to convert stresses from their general form to the principal values. So another more direct way, which is preferred in some quick calculations, is that the equivalent stress for 2D can directly be obtained using this formula. So this is, instead of having differences, as you can see here, then it's just sigma x squared plus sigma y squared minus xy plus 3 tau xy into the 1/2. So if I have this recorded somewhere, then I can use it directly. Or if it is in 3D, in the rare case that we have 3D, then another formula for sigma equivalent that includes the shears is already here. Like if you have this formula here that I'm going to mark, is the most general one, because if the shears are 0, then the sigma x and sigma y, sigma z will be just the principal stresses. Otherwise, if the shears are there, I don't need to make transformations, and I can use this formula directly. So the end result is that I can now plot this equation, which is the yield surface based on distortion energy, on the 2-dimensional plot, and it gives me an ellipse, and the ellipse encloses the Tresca hexagon, and that's great for ductile materials. The next one is Mohr theory, and Mohr notice that if we have semi-ductile materials like cast iron, for example, then in compression it has a lot more strength than in tension. So if we use just the maximum principal stress criterion, then we would be over-designing it if it is used in compression applications. So with this idea, Mohr just decided to figure out if I have my circle here for pure tension, and then I have my dotted circle here for pure compression, which is at minus S compression, that is much larger than S tension. So if I have these two extremes and I know they work, what happens if I have something in between, like a circle that has some kind of stress state that is in between? So the simplest approach is to just use geometry and have a tangent line between the three circles, and then from similarity of the triangles derive the condition for Mohr theory. I have in the lecture. So the end result is that of this step is that we end up with three cases like we did for the maximum shear theory for the A and B and the zero. So the zero is here, zero in the middle, zero in the back, and the first location. And when it's in the first location, then it means that it's a compressive state. Then sigma B is less than or equal to minus the compressive strength of the material, which is pretty high. And for zone 1, sigma A will be greater than the tensile strength of the material, which is low. But in between, you get an equation of straight line, but it is not exactly 45 degrees because the tension and the compression are different, the strength. So you end up modifying the maximum shear theory. Instead of being a box exactly, then the box has one part small, one part big, and then you connect with straight lines. So the equation of this straight line is right here. This equation here is the equation of this straight line and also the equation of this straight line. So this is the equivalent for quadrant 2 and 4 of the maximum shear theory. You guys can stop me if I'm going too fast because I'm kind of reviewing the lectures. Okay, so if there are no questions, I can continue. So we have an example here. An example is that I have a 25 millimeter diameter shaft, and I have a torque applied to the shaft, 230 Newton meter, and it's made of cast iron, and this is the designation of the alloy, cast aluminum, sorry. And the cast aluminum has a yield strength in tension 160 and in compression 170. So in compression it's a little bit better than tension, but not by much. So anyway, we want to find out the factor of safety for this case. So step 1 is to convert forces to stresses. And luckily, the force system is very simple. It's a torque. So the tau, the shear stress that results is this magnitude, 16T over pi d cubed. And that comes from T times R, which is D over 2 over J. So when I do the conversion, I get this result because in the form of J. And that gives me 75 MPa. So it's a pure shear state. And if it is pure shear state, I don't know how to represent it on the principal stress state because the plane that we are working on has two axes, sigma A and sigma B. And these are the two non-zero stresses of the three principal stress system that we have. And here we have neither, we have only shear. So we have to go from shear to the principal stresses. And the trick here is not to do any transformations, it's to use the knowledge that if I have shear, pure shear, so this is important knowledge like this. If I have a pure shear stress, then this is equivalent to a biaxial stress state. One value is positive and one value is negative of the same magnitude. So this is, that comes from Mohr circle transformation, but the end result is this here. So if you are in a hurry and you don't want to do stress transformations, then you have to know this bit of information that pure shear is equivalent to biaxial. As we know, if you have biaxial, you have one stress here and then one stress of exactly the same magnitude, but on the other direction. If you just transform, if you rotate this element element 45 degrees, then the rotation will give you an element that has only pure shear. So these two are equivalent. Is this okay?
Yeah, that's good. Thanks, Professor.
Okay. All right. So with that, since the strength and tension is slightly different from compression, I might as well. I could have used the standard maximum shear criterion, but here, since I have two different values, I might as well use the Mohr criterion, ductile Mohr, called ductile Mohr. So instead of sigma 1 over sigma S yield minus sigma 2 over S yield, we just change S yield and tension, and this is S yield and compression equals to 1 over N. And then I have sigma 1, I put it here, and sigma 3 is, I put it there, and I use the two numbers they gave me, and I solve for N. So the safety factor comes to be 1.1. Another way to do it is to look at the graph. And the graph here, when you have pure shear, then the pure shear line, the load line, is at 45 degrees, like this. So the load line will intersect the equation describing the yield boundary at a point, and the solution of these two, because we have one straight line this way, 45, and then another straight line that we have the equation for. If we solve these two straight lines, then we find the coordinates, and it gives us this value for the value of the shear strength at yield. So it's kind of a geometric mean of the shear strength and compression tension, and that I can use this fact in a different way. So I can just go, instead of finding the principal stresses as we did with transformation, I can use it directly, and again it gives me the same factor of safety of 1.1 if I use this criteria. All right, so this is as far as we have here the results that we talked about. I think this is it here for the various ductile failure theories. So now I'm just going to review a little bit of the follow-up on that for brittle failure. So brittle failure is small modifications. So brittle failure, the first theory is maximum normal stress, and the maximum normal stress is, we recognize brittle from ductile is that when you have brittle material, it doesn't have a yield point. So it breaks immediately at the ultimate strength right away. So it doesn't have, we know in ductile you go to the yield, and then from yield you go to the ultimate. But brittle, it just goes directly to the yield coincides with the ultimate. So you modify all of the previous theories. Instead of yield, it will be just sigma A greater than sigma ultimate, with sigma B less than minus sigma ultimate in compression. So if you have now the maximum normal stress theory, it will be this line. So let me just take another line here. So if I translate this to maximum normal stress theory, then it will be a box, but it will be a box. It has one side at S ultimate tension, and the other side is at minus S ultimate compression. So it's exactly the same as the ductile yield, except that we have two values of the one for tension and compression, and then we don't have yield, we just have ultimate. So that will be the change that we would have. Then the second criterion is here here we call it brittle Coulomb Mohr. And brittle Coulomb Mohr, we have the same box as we did, like here, but in region, in quadrant 2 and quadrant 4, we would have straight lines, so it's exactly the same as in ductile. The only difference is that in ductile, we use the yield, and here we use the ultimate. So you just substitute the letter, the subscript Y with the subscript U. That's all what it is here, up to this point. Okay, so this is brittle Coulomb Mohr. Now, the problem with the brittle Coulomb Mohr is that it is kind of not taking advantage of the fact that the material is actually strong in compression. So in order for us to take advantage of this, then we can modify it and extend the failure zone a little bit more into the compression region. So instead of going directly with this line here, we just will extend it as if it is maximum normal stress criterion here, and then we can deal with the shear with the straight line. So we'll have to modify the equation for the straight line of the Coulomb Mohr in the case of when we have shears, but we just extend it out, and therefore it turns to be a little bit more involved, because in this case the regimes are the same. The first and third regime are the same as we learned before, but the second regime splits to two parts. One depends on if sigma B is less than sigma A or sigma B greater than sigma A, because that determines whether your point is actually here or your point is right there. So if you have it here, then it's sigma A less than sigma B. If you have it here, then sigma A is greater than sigma B. So depending on where the point is, then we can use either this limit here or this limit here. And this is in one of the problems that I'm going to show. So let me just take an application in here. An application is an example. We might have seen it. But in this example, we have an assembly, and the assembly is attached to fixed part of machinery, and it is like a shaft, step shaft, and the step shaft has an arm, and the arm has a force on it to induce both torque and bending. So the worst point is point A. And the reason we judge this worst point because there might be another point here that has higher bending or higher torque, but we know that the force F is going to induce a torque which is the same for A and whatever other points, and then this force is going to induce bending. So the bending moment at A is less than the bending moment at the base of this assembly. However, point A is actually has a stress concentration because the cross section is smaller. So I made a judgment as a designer right away that I'm going to analyze point A because it has the highest probability of failure because the cross section is smaller, it has high stress concentration, and then I ignore any other points. So the first step is to translate from forces to stresses. And here we have the stresses are two. One is axial and one is shear. The axial is due to the moment, so I have to estimate the moment from the force by taking the moment of this force about this point here. So there's a distance between these two, this 12-inch, and that gives me sigma x. Sigma x is axial. It's axial. It means that it is actually pulling the material in this direction. That's due to the bending. And then I have now to also determine the shear. The shear is due to a torque here. So the torque is the force times this arm length. It's a different arm length. And here, for lack of knowledge of the stress intensity factors, if they're not given to me, then I'm going to assume that for the time being, the stress intensity factor for tension and shear are 1, because I don't have any other information. In reality, as a designer, I look at the design tables and then I can determine the stress intensity factor that will amplify the stresses somewhat. So this is step 1. As I mentioned, it takes a little time, and up to this point is analytical, right? Because this is why we have developed all of these formulas. In your project, you can get the stress distributions numerically. And in real-life design, this step is the finite element step where you do all meshing and you go to look at the stress tensor everywhere, and then you determine the point that has highest probability of failure to be the one that has high maximum stresses, for example. So here, since it is analytical, we are just using calculations to get the two principal stresses, the non-zero stress, sigma A and sigma B, and this is basically more circle stuff or stress transformations, and that gives us two values of stresses, 175.8, but they're all in terms of F, the force applied F, and the other one is minus 33.2 in terms of the force F. And the question was to determine that force F. Once we know the material properties, we know the ultimate in tension and the ultimate in compression, and then since they told us it's cast iron, then it triggers in my mind that it is going to be a brittle material, and therefore it's corroborated with the evidence that the ultimate in tension is much smaller than the ultimate in compression. So I immediately have to go to brittle Coulomb Mohr or modified Mohr. So I can just assess both cases here. So that's what we did. And here, if we use the brittle Coulomb Mohr, then we use the equation of the straight line and solve it for a factor of safety of 1. It gives us the force to be 167-pound force that corresponds to a factor of safety of 1. However, if I do modified Mohr, then I have to check on the ratio of B to A. And I find that this ratio is less than 1, and therefore it is as if I'm applying the maximum normal stress theory, which means that I just sigma A over sigma ultimate in compression is what matters. And that ultimate in tension, rather, ultimate tension. And therefore, like this effect of this part is not there because of it's a modified Mohr. So it's a little bit less conservative, and we get a value of the force of 176. So the last part of this review is that how do we select the failure criteria? And I have it here to determine first I have to decide whether the failure criterion is to be selected for a brittle material or a ductile material. So that's the decision about it. So if I'm doing, let's say, programming, or I'm doing general design, then I have to look at the database for the material and then find the strain at failure. Epsilon sub F is the strain at failure, epsilon F. So this is an important point, and the value tells you a lot about the material. For example, if you have a very good ductile steel, the epsilon F could be 60 or 70%. So it stretches a lot. It's like rubber before it fails. But if we have cast iron, the epsilon failure could be 2-3%. So roughly speaking, from a design perspective, we divide it. Less than 5% go this way, above 5% go this way. So that's kind of the delineation, rough delineation for designers. And if it is less than 5%, then I have to select. I can select depending on the level of conservatism, as you've seen from the previous example. If I want to be conservative, I can use Brittle Mohr. And if I'm sure about my experimental data with less conservatism, I can just use the modified Mohr. So that is consistent with these results. This is modified Mohr. This is Brittle Mohr. And obviously, modified Mohr is a little bit less conservative than the Mohr. So that's kind of the first step for me, is to make the decision brittle or ductile. Once I decide, let's say it's ductile, going this way, then I check to see the yield intention. Is it the same as the yield compression? If it is yes, then I know that it's a symmetric yield surface. If it is no, then it's not symmetric yield surface. So if it is yes, then again I decide if I know the data. If I don't know the data, then I go to be conservative, and the conservative is the maximum shear stress theory, which is inside the ellipse. So the hexagon is inside the ellipse, so it is more conservative because you're limiting the space for yield. And otherwise, if I have good data, then I can go this way, and I use the distortion energy criterion. Now, for most of the codes like COMSOL, when you interrogate it, then you'll find that you can plot pretty much the distribution of every component of the stress tensor everywhere. But for failure, it's much easier to select a representative, which is the equivalent stress or the von Mises stress, and then compare it to the yield strength of the material. That's kind of the easiest approach to determine if you have yield at the point. And then again, if the yield intention is not equal to the yield of compression, then I use the ductile Mohr, where everything instead of ultimate is just the yield in this case. So that is what I have in terms of a review, and I wanted to see if you guys have any questions before we talk about some other things. Okay.
Yeah, I don't think I have any questions.
All right. So I'm going to discuss just a couple of problems from the homework assignment, just to see how we would think about them. So let's just do that to help you with the kind of thinking process. And I choose 521, for example, to 25, this group of problems here. So if we read it, we have an ASTM 30 cast iron. We want to find, so we know the properties from the tables at the end of the book. And we want to find the factors of safety. And the factors of safety, when we use it, we use the Brittle, Mohr, and the modified Mohr theories because it's cast iron. And not only that, but we want to plot the failure diagram in the sigma A, sigma B plane, which are the two non-zero principal stresses. And then we want to locate the coordinates of the stress state, which is the point of the stress state. And then number C, we want to estimate the factor of safety from the two theories graphically. So we have different problems here, the same objective. The only difference is that the stress state is different in all of these problems. So let's just discuss the idea. If you take 521, for example, you have a sigma x of 15, sigma y of 10, and tau xy of 0. So you ask yourself, can I represent this on the sigma A, sigma B plane or not? Well, the answer is that you can go ahead and represent it on the sigma A, sigma B plane because since there's no shear, it means that this actually is sigma A and this would be sigma B. So you have basically sigma A and sigma B directly computed, which are the two principal stresses. Okay, so if you take another problem, like let's say this one, then you see that you have a shear component, which is the -10. So what do we do then? Well, we use the Mohr circle transformations to find sigma A and sigma B, as we learned in class. So that we have to find sigma A and sigma B. So they're going to be, these two are going to be different from this one and this one. So they'll be different. But we know how to find sigma A and sigma B. So these are giving me the coordinates. And then from the ASTM grade, at the end of the book, I have to find S ultimate in tension, S ultimate in compression from the data. And the Brittle Mohr is the box that we've defined. It has, that we talked about before with two straight lines on the sides directly. And the modified Mohr, you extend the box a little bit on the quadrant 2 and quadrant 4, and then you connect with straight lines. So this is the procedure, and quickly show how it looks like. Just quickly show you just the idea without going into too much detail because I would like you to work it out, that you get something like that. So you have to do a graphical representation according to this problem. There's your box that is asymmetric, because tension compression is symmetric. And then here's the straight line. If you have Mohr, if you don't have Mohr, you want to modify it, then you go down to the same level of tension, and then you connect to a straight line. So these are the first determination of the boundary, which is the the failure surface, not the yield surface, failure surface. And then depending on the problem, you have coordinates of points, A, F, K, C. All of these are points for different problems after you do the stress transformations to find your sigma A and sigma B. And then to compute the factor of safety, for example, you have to find this length here and then this length there, and then divide these two lengths by each other to get the factor of safety. So are there any questions on this one? Okay. All right, so the last problem I wanted to discuss is problem number a little bit later in the chapter, and that's problem that 570, I think, is the problem here. This one here. So this problem is I have a tube, and the tube has an inner member and an outer member. So this is like a shrink fit problem. So the inner member has an ID of 1 1/4 plus or minus 3 mils. And the outer member has an ID of 2.001 plus or minus 0.4 mils. Very, very small. And then the inner member has an OD, as you can see here, and with the bilateral tolerances indicated there. So that this is a real manufacturing issue. Like when you buy tubes, this is what you would get. And then now, if we want to press the inner member inside the outer member, the inner member has an OD of 2.002, and it's not going to fit exactly here. So there's a difference between these two, as you can see here. Not only that, but there's a probability that this inner outer OD can be even larger by that amount, because this is the tolerance, and then the inner can be smaller by this amount. So things can be worse. So we have a range, basically. So, however, what they wanted us to do is that they wanted us to find the nominal shrink fit pressure when we put one inside the other. So when you say nominal, it means that they wanted just the average. Like you have an average value of the ID and average value of OD, and you put them together. So that value, that the nominal now, the difference between these two is 1 mil, and this is difference in the diameters. So the delta for the shrink fit is half of that. So it'd be half a mil nominally between the inner member and outer member. If they had asked us for the worst case scenario for design, then I have to consider the worst case here and the worst case here and subtract and get the largest possible difference that can cause internal pressure. So anyway, so the first step is to find the pressure. And then once you find the pressure, then you want to find the von Mises stress. And in these problems, the tube, we have a formula. If you give me the interference delta, which is half a mil, I can just plug it into the formula and get the interfacial pressure. Once I get the interfacial pressure, then I can forget about interference. I can think now as if I have two separate tubes. The inner one has an external pressure trying to implode it in, and the outer one has the same pressure but tries to explode it out. And then I compute the values of the stresses in each tube. And it turned out to be that each tube is a thick tube. So I have to use the thick tube formulas, and that means that I have to find the tangential stress and the radial stress, the highest tangential stress and the highest radial stress. from which I can find the von Mises stress. So it's several steps again. The steps are following the same situation that you get. First, you convert forces to stresses, and now you have to think a little bit harder because you have to find where the stresses could be the highest and how you can combine them to find the von Mises stress and determine if you have any failure. So that's kind of the situation here. And quickly, if you look at it, I think maybe here. So the step that I talked about verbally is right here. This is the nominal interference. So it's very small, 0.5 mils. And then for each mil, then for each delta, I have the pressure. So the pressure is the delta, E delta over 2R cubed, and then you have this function. And we plug in the R inner and R outer, and that gives me the pressure. So if you look at the pressure, it's 3,000 pounds per square inch. And that's a pretty significant pressure. Like typically tubes in design applications, if we're lucky, they can carry 1,000, 2,000. So when it gets that high, it means that it's going to be under good stress, good amount of stress, unless it is thick, which it is the case here. So you take that and then you convert it now. So you have the inner one has this kind of pressure on it, and the outer one has the opposite pressure. So exactly the same, but the opposite. So this is outer, and this is inner. And then you have the formulas for the tangential stress and the radial stress. So you have two values. And then you know how to combine them now to get the von Mises using the formula that I discussed earlier in the lecture. So you get the von Mises stress right here. So the rest is very similar with some variations that I'm going to let you work on it. But I just wanted to show you some of the methods of thinking about these problems. Okay, so that's all what I have really, and I don't know if you guys have any questions. I would be happy to answer any questions here. Daniel and Stephen, are you guys still there?
Yeah, I'm here.
Yeah. Okay. Yeah. Any questions?
I don't think so this time. I was just trying to think over what you talked about. So yeah.
Okay.
Could you briefly just go over von Mises stress? Remember exactly.
Okay. Yeah. The von Mises stress is so the von Mises stress is the way that we derived it is we derived it based on the distortion energy exceeding its critical value. And the end result of this is that we found a representative stress, which is given by this formula. And this representative stress, we're going to call it the von Mises stress. So this is the original way that you find the von Mises stress if you know sigma 1, sigma 2, and sigma 3. However, we know that sigma 1, sigma 2, and sigma 3 could be equivalent to the original stress tensor. The original stress tensor had sigma x, sigma y, sigma z, tau xy, tau yz, tau zx. So this is 6 of them. So 3 are equivalent to 6. That's the idea of transformations. So I can find the equivalent stress directly from the 3 if I know the 3, or if I don't know the 3, I just know all of the 6 of them, then this equation here is exactly equivalent. So it gives you the same magnitude as if you knew the principal stresses. In other words, if I substitute for sigma 1, sigma 2, sigma 3 from the values of the x, y, z, then what I would get is this formula. Is that clear?
Yeah, that's